Well, happy Wednesday. So as I mentioned today, as I mentioned, what we would do today is look at reviewing environmental chemistry for the FE exam. I have set this up that we can do it as a poll. We cannot, it's kind of up to you. This is your review. So please feel free to ask questions, make comments. I'm hoping over the summer to put together a few others of these, which I'll post online, or if you'd like to do them in person, we can figure out how to do that. Just let me know what's best. The environmental chemistry section covers the material that's listed here. Stoichiometry, chemical reactions, so that includes equilibrium, acid-base reactions, redox reactions, precipitation reactions, and PC-pH diagrams. We won't be able to cover all of this, but we will cover much of this. Kinetics, we've done quite a bit in terms of, in the context of mass balance, but we'll look at a couple kinetics problems today. Organic chemistry, predominantly just nomenclature. We won't have time to go over that. But basically, it's really covalent. What is covalent bonding? Knowing that, for instance, in organic chemicals, the carbons are covalently bound to one another. That type of, there may be that type of question, and then some questions about nomenclature. And then lastly, multimedia equilibrium partitioning, and we'll talk a little bit about that. So just quick review in terms of terminology that's used in chemistry. So atomic number is the number of proteins in the nucleus of an atom, and all atoms of a particular element have the same number of protons. The number of neutrons and electrons can vary, but the number of protons determines the atomic number and therefore determines the element type. Isotopes are chemically identically forms of an element, and they have the same atomic number, which means that they have the same number of protons. The number of neutrons will change or can change. So for example, we can look at this in terms of carbon. So the atomic weight or the atomic mass is the average atomic mass for the naturally occurring element. So carbon 12 is defined as having 12 atomic mass units, 6 protons and 6 neutrons. But if you look at a table of atomic masses, you'll see that carbon is listed as having an atomic mass of 12.01. And the reason for that is that in nature, there's a small percentage of atoms or isotopes that have 7 or 8 neutrons. And the atomic mass that's listed in these tables is a weighted average of the atomic masses of all of the isotopes. So that's why if you look at a periodic table, look at a table of atomic masses, you'll see that carbon is listed as 12.01. The molecular formula is the chemical formula that gives the exact number of different atoms found in an element. So for example, octane is C8H18. So all of the carbons are single, have a single bond. And we would have 8, 1, 2, 5, 6, 7, 8. And I haven't written the hydrogens, but these would all be hydrogens. And the atomic mass is simply the it's the mass of a mole of a particular substance. So for octane, we have 8 carbons. We have 18 hydrogens. The atomic mass of hydrogen is 1.008. So the atomic mass of octane is 114 atomic mass units, or we will often write this where we're talking about grams per mole. And a mole is defined as Avogadro's number of molecules of a substance, and that is 6.022 times 10 to the 23 molecules of a substance. So when we just looked at octane, that has 1 mole of octane as 6.022 times 10 to the 23 molecules and would weigh 114.22 grams. Varies significantly with compounds. Something hydrogen, H2. So a mole of hydrogen would be 2 times 1.008 or 2.016 grams. On the other hand, and I really never thought about this until recently, somebody had posted this on Twitter, that a mole of DNA or RNA is actually several kilograms. We don't think about it that, but because the molecular weight on such a large molecule, a mole of DNA is on the order of kilograms. Now we can also talk about kilogram moles, we can talk about milligram moles, and often we'll use this as milligrams per millimole. We could use this as kilograms per kilomole. And then we've got grams per mole. And it's really a gram mole, but we almost never write gram mole. The other thing to remember is the ideal gas law, PV equals nRT. We've used this this semester in 489. And then remember that volume times pressure divided by temperature is equal to volume times pressure times temperature. I started to say vice president, and it's because when I was in high school, we learned this is vice president over treasurer equals vice president over treasurer. Just a little way to remember it. Just like with redox chemistry, and I don't have anything in here on redox chemistry, but we learned Leo the lion goes grr, and that's lose electrons oxidation, gain electrons reduction. So if you can't remember which is which, just remember Leo the lion. He goes grr. I can do this as a poll. Actually, I'm going to do this one. Okay, I'm going to launch this one as a poll. So we have the pressure of a constant mass of an ideal gas is halved, and the absolute temperature is doubled. So the volume is, if we half the pressure, but we double the absolute temperature, remember temperature is in Kelvin, the volume is, so most of you said constant, okay? The answer is quadrupled. So we have volume times pressure over temperature is constant. And so the mass is not changing. What we're looking for is the volume, and the volume is equal to temperature over pressure. And we've doubled the temperature and we've halved the pressure. So the volume increases by 4, by a factor of 4. So remember, okay, that volume times pressure divided by temperature is constant as long as the mass is constant, which is what's stated here. Another aspect on the FE is stoichiometry. And stoichiometry is just that part of chemistry that's concerned with how chemicals react or the proportions of chemicals that react. And so it provides us information not only about what is reacting with what to produce what products, but also how much of those reactants are reacting and how much of these products are formed. So if we consider this problem here, so we have arsenite reacting with carbon to produce carbon monoxide and arsenic. You're given the atomic weights, and you're asked, okay, according to the equation above, the reaction of 1 standard gram mole of arsenite with carbon will result in the formation of. And we can do this one as a poll also. So let's think about this. Most of these problems are actually, or many of them are, they're very similar to the format, as I mentioned on Monday. This is the type of format you'll see. It'll all be multiple choice. So the answer is 150 grams of arsenic. And let's just look at this problem. Now, the problem doesn't state it, but in order to do this problem, you do need to think or make an assumption that carbon is in excess. So we have, I'm just going to write it up here. We have 1 mole of arsenite. We'll assume that the carbon is in excess. So we produce 3 moles of carbon monoxide. So the molecular weight is approximately 12 plus 14, or 26. So if we have 3 moles times 26 grams per mole, that's equal to 78 grams. And then for arsenic, we have 2 moles that we form, and arsenic, you're told, has an atomic weight of 75 grams per mole. So that is 150 grams. So that is the correct answer. And this cannot be true because, as we just showed, okay, we have almost twice as much arsenic formed than we have carbon monoxide. So you're given a balanced equation, and you're just assessing then or calculating how much mass of each of these substances are produced. So for this problem, it's a little more difficult because you have to balance the equation. And here you're asked, you're designing an aerobic system to biodegrade benzene. The biodegradation follows a chemical reaction below, but you must balance this equation. And the benzene concentration is 500 milligrams per liter. The amount of oxygen that must be consumed to completely biodegrade the benzene is most nearly, and this is in milligrams per liter. You can do this one as a poll. So we'll let you think about this for a bit. So you first need to balance the equation. Okay, in the interest of time, I'm just going to stop here. Okay, so the first thing we need to do is balance the equation. And the answer is 1600. So we have, let's just keep track of the various different elements. So we have carbon. Start with this. We have 6 carbons on our left side. So we need 6 carbons on the right side for the products. My advice here is always balance oxygen last because it's not combined with any other chemical. So we have 6 hydrogens here. So we need 6 hydrogens here. We multiply water by 3. We have 6 hydrogens. Now balance the oxygens. So we have 12 oxygens plus 3, so that's 15. We need 15 here. So in order to do that, we will multiply this by 7.5. We need the molecular weight of benzene. So the molecular weight of benzene is equal to 12.01 times 6 plus 1.008 times 6. So it's just the atomic weights of each of those elements, and that is 78.048. And that is grams per mole. But we're going to use milligrams per millimole, and that's because the concentration is in milligrams. So it makes it easier. We have one less conversion to do. So if we have 500 milligrams per liter, we divide that by the molecular weight of benzene, and that is equal to 6.4 millimoles per liter of benzene. So the amount of oxygen we need for every 1 mole of benzene, we need 7.5 moles of oxygen. So we have 6.4 millimoles per liter, and this is benzene. We need 7.5. We can do this as millimoles of oxygen per millimole of benzene. And then we can multiply that by the molecular weight of oxygen, which is 32 milligrams per millimole. It's O2. Millimoles of benzene cancel, millimoles of oxygen cancel, and we're left about 1,540 milligrams per liter, and the closest value is 1,600. So you'll find sometimes that the numbers don't quite come out to what you have calculated. It's not necessarily that it's wrong. They may have calculated the molecular weight a little differently. They assumed it was 78 instead of 78.05, made some other estimates in there that'll give you a slightly different answer. So don't assume that your answer is wrong if you don't get the exact answer that they've provided. Feel free to stop me if you have any questions. Okay, the next thing we can look at is chemical equilibrium. So here what we're talking about is, okay, we have a chemical reaction that is occurring. And so we can write this, for instance, we have calcium carbonate dissolving in water to form calcium and carbonate. And the calcium carbonate is solid. And if we have an excess of calcium carbonate and we add those, that reaction continues over time. It doesn't really stop, but we've got some calcium that is dissolving, some calcium that's precipitating, and this reaction continues over time so that the net composition doesn't change. And when that happens, we state that the reaction is in equilibrium. Shown here is with the reaction of hydrogen and iodine to produce hydrogen iodide. And what you see, if we start with the left-hand reaction, we initially start with hydrogen and iodide, and those two react to form hydrogen iodide. And at some point in time, the concentrations are constant and the reaction is at equilibrium. If we start with hydrogen iodide, note, now the reaction will proceed, in which case hydrogen is formed, iodide is formed, and note, if we start out, in this case, we're starting with twice 2 moles of hydrogen iodide, we end up at exactly the same place. So it doesn't matter where we start. The ending point is simply based on the equilibrium reaction, or the equilibrium constant for that reaction. And we can write an equilibrium expression for this reaction. So it's products, always remember, it's products over reactants. So it's hydrogen iodide squared, because we have a stoichiometric coefficient of 2, divided by hydrogen, and this is a stoichiometric coefficient of 1, because this is really a 1, and iodide is also 1. There's an implicit 1. And we can write a general form for the equilibrium expression, and it's just A moles of A reactant plus B moles of B react to form C moles of C plus D moles of D. Remember, when you're using equilibrium constants, your concentrations must be in moles per liter or molar units. Cannot use millimoles, cannot use micromoles, cannot use kilomoles, use moles. That's how it's developed. That's how the equilibrium constants are defined. So considering this equation, the reaction above is the formulation of what equilibrium reaction? Our products are what? Write it in the chat. What are the products? Or what are the reactants? Remember, it's products over reactants. So our products are C plus D and A plus B. Stoichiometric coefficient then is 2. 2 is 4, and this is implicit as 1. So if you had a problem like this, they would give you a series of equilibrium equations or reactions, and then you would pick the appropriate one. Remember that the equilibrium constant is a property of the chemical species, and the reaction, it's based on thermodynamics. It depends on temperature and pressure, but not much else. And these are valid only if the system is at equilibrium, but many natural systems are not. There are also a number of special cases. Now, these are actually developed not for molar units, but for activities. We use molar units. In those of you that took 481, you've done some calculations there where you looked at activities. But the way we define these reactions, and remember, this is a set of notation that was developed by physical chemists, and they had to agree on a set of rules. And one of the rules that they agreed upon was that for water, the activity is 1. So for instance, we typically write this with these types of brackets, and the activity then of water is 1, so that water does not appear in the equilibrium expression, which is why when we write the equilibrium expression for the dissociation of water, we don't include water in the reaction. The other rule that was agreed upon was that the activity of a pure solid is 1. So the activity, for instance, here is written as calcium carbonate, as a pure solid is equal to 1, which is why your solubility products do not have the solid in the equilibrium expression. So this is just a rule that was agreed upon. Just like when they developed algebra, they decided that if you multiply a positive times a positive, you get a positive. If you multiply a negative times a negative, you get a positive. And if you multiply a negative times a positive, you get a negative. Those are rules that were determined when they developed the set of mathematics we know as algebra. These are just rules that were developed by the physical chemists. So the concentration of calcium in pure water that is equilibrated with excess calcium sulfate, and this is a solid, gypsum, known as gypsum, is most nearly, and I'm just going to add the S for solid, and we'll let you try that one. So the concentration of calcium in pure water that is equilibrated with excess calcium sulfate is most nearly, and you're given in this case the solubility product. The reference handbook also has a list of solubility products. Okay, in the interest of time, we'll stop there. The answer is 200. So we can write this as concentration of calcium times the concentration of sulfate is equal to the equilibrium product. Note, I didn't include calcium sulfate. We'll assume that it's a pure solid. In all of these problems, you can assume that it's a pure solid. We start out with pure water, so we have no calcium or sulfate in that water. So that means that when that calcium sulfate dissolves, the concentration of calcium has to equal the concentration of sulfate. So if I substitute, I have calcium squared is equal to 2.4 times 10 to the minus 5. And that means that the calcium concentration is equal to 4.9 times 10 to the minus 3. And your units are molar units. So that is 4.9 millimoles per liter. And I just did a conversion. Okay, if it's 10 to the minus 3 molar, that's 4.9 millimoles, and that's 40.08 milligrams per millimole. And that equals 199 milligrams per liter. I could have left this in molar units, in which case I just would have had 4.9 times 10 to the minus 3 moles per liter. I'll multiply that by 40.08 grams per mole, but I wanted this in milligrams, so 1,000 milligrams per gram. Grams cancel, moles cancel, and I'm left with 199 milligrams per liter. So I'm left with the same result. Whatever is easier for you in terms of working these problems. You may also see problems looking at reaction order. So note here, this is the table from the reference handbook, and you're given the equations for both for zero first and second order reactions. You're also given equations for whether it's a batch system, an ideal plug flow system, or a completely mixed flow reactor, or a CSGR. So get those equations if you need them for solving these types of problems. You may also see problems where you're asked about to calculate a half-life, or to use the half-life to calculate the concentration. And the half-life is just determined from the fact that, or it's the time that is required to reach 1/2 the initial concentration. So it's written here that CT is equal to 0.5 C naught. So if we substitute, we end up with natural log of 1 over 0.5, and that is equal to K times the half-life. And your half-life is simply equal to ln 2 or ln of 0.5 over K. So it depends whether it's growth or decay. If it's growth, it will be positive. If it's decay, it will be negative. We can look at a problem here where we have a storage tank that contains a chemical that degrades according to first order kinetics, and we have a half-life of 10 years. The chemical concentration is 300 milligrams per liter, and you're asked what is the concentration after 1,590 days. So K is equal to 0.693 over T to the 1/2. We have 0.693 over 10, and this is 10 years, times 365 days per year. So we'll end up with inverse days. That is 1.9 times 10 to the -4 inverse days. I didn't use the negative. Major thing is to think about whether you have decay or growth. So if we write this in terms of C sub t, that is equal to C at some time t is equal to C naught e to the minus kt. So I've written this in terms of decay. If we had the formation of a chemical, then if we have formation, then you want to write this as Ct is equal to C naught e to the positive kt, because we have concentration increasing. And this is equal to 300 milligrams per liter times e to the minus k, which we just calculated as 1.9 times 10 to the -4 inverse days, times 1,590 days, and I apologize for the extra lines, and that is equal to 40.3 milligrams per liter. So 40 is the correct answer. If you have a problem that pertains to BOD or biochemical oxygen demand, it's a first order reaction, but be careful. And the equation, this information is actually provided in the reference manual, but remember that L naught is your ultimate BOD. So for instance, if we plot BOD versus time, typically have an exponential curve, reaches and asymptotes at the ultimate BOD or L naught. So at some point in time, there's a certain amount of BOD that is exerted. And there's actually a certain amount here that is BOD is left that can be exerted if we leave it long enough. So BOD at any time is equal to the ultimate BOD times 1 minus e to the minus kt, where k is your BOD decay constant, typically in inverse days. L naught is that ultimate BOD, and time is in days. So for instance, we often use a 5-day BOD. So that is equal to L naught times 1 minus e to the minus k times 5 days. And the reason for the 5 days is just historic. It happens to be the average time for water to reach the sea from London. And it's because the test was actually developed there. And originally it was 18 degrees. Test was run at 18 degrees, and that was because that was the average temperature of the River Thames. It is now standardized to 20. So in the interest of time, I'll just work through this problem. So we have a municipal wastewater treatment plant, and you're told that it has a 5-day BOD of 200 milligrams per liter. And you're told that the BOD rate constant is 0.23 inverse days. And you're asked for the ultimate BOD. So we have BOD 5 is equal to L naught 1 minus E to the minus K times 5 days. And this is 200 equals L naught 1 minus E to the minus 0.23 inverse days times 5 days. And L naught is equal to 292 milligrams per liter. So 292 is the correct answer. We're running out of time. I've got about 4 more slides. If it's okay, I can continue and we'll just finish this up. So just some perspective on rates. One, remember that rates are always temperature dependent. They use Arrhenius equation. You probably will not have to deal with that on the FE. And rates depend on the reactions and pathways. The composition of the system is important. However, as I mentioned, you shouldn't have to deal with that on the FE exam. The other thing you may see are problems related to Henry's law. And this just says that the amount of a dissolved gas in a liquid is proportional to the partial pressure in the liquid. So for instance, if we look at CO2 aqueous, and it's written here, that concentration is a function of the partial pressure of CO2. Same thing for oxygen. We can write the same thing. Concentration of oxygen in a liquid is a function of the partial pressure of oxygen in the gas phase. And at low concentrations, it's linearly proportional. So we can write an expression like this that says the concentration of CO2 is equal to Henry's constant times the partial pressure of CO2. In this case, the Henry's constant is given in moles per atmosphere. Be really careful of the units. It's an empirical constant. And in some cases, you'll actually see it written the opposite way. So you'll see it written as pressure over concentration, aqueous concentration. You'll know that by the units. So just take into account the units. The last thing that we'll look at today are partition coefficients, and this really pertains to bioaccumulation. So many organic chemicals are highly hydrophobic, hydro meaning water, phobic meaning fearing water, so they don't want to be in water. And those chemicals will typically partition to other phases. So for instance, in the cells, in the fatty tissue, this is the case with a group of chemicals known as PCBs, polychlorinated biphenyls. They're extremely hydrophobic and they accumulate in the tissue of organisms. Because of that, and we're concerned with this partitioning, and it's hard to describe it in terms of cells. We've often used the octanol as a surrogate for biomass. Behaves somewhat similar. So in the way it's written here, it's just a general equation for a partition coefficient. and it just says that K is equal to the concentration in the organic phase over the concentration in water. So for an octanol water partition coefficient, that is the concentration in the octanol divided by the concentration in water, and these are determined at equilibrium. So it is an equilibrium constant. But these are determined experimentally, they're not based on thermodynamics. And the FE gives you a number of these. They give you a bioconcentration factor, which is actually specific for an organism, a octanol water partition coefficient, which I just gave you, and then a organic carbon partition coefficient, which is based on the organic carbon in soil or sediment. So the last problem we'll do here is we have an equilibrium concentration of paradichlorobenzene in the aqueous phase of a two-phase system where we have octanol and water. Octanol doesn't dissolve readily in water, so that's why it's two-phase. And the concentration in the water is 21 micrograms per liter. And the log KOW, and typically your KOWs are given in log values, is 3.370. And you're asked, what is the concentration of paradichlorobenzene in the octanol phase? So remember, we have KOW equals the concentration in octanol divided by the concentration in water. So KOW is equal to 10 to the 3.370 equals the concentration in octanol divided by the concentration in water, and the concentration in the octanol is equal then to 49,000 micrograms per liter. This asks for it in milligrams per liter, so the answer is 49.2. So we will end there. And if anybody has any questions, happy to answer those. But this ends classes for the semester. So have a wonderful summer. For those of you that are graduating, congratulations. And to all of you, may your futures be bright.